All right. So you guys, I think you guys have an average of 75.2% on this one. All right. Yeah, four of you guys in the 90s, three in the 80s, and two in the 70s. Four of you guys have 60s, one 50s, and one less than 50. Okay. I just put it the solution online so we can take a quick look on that. Okay. So on the first one, this is just ideal gas law for the same gas in two states. So PV equal to nRT, you can rewrite. So PV over T will be equal to N times R. So PV over T will be equal to constant. That means initial equal to final. Okay. Then you can calculate for your P final because the rest are given. All right. Either like they are given in values or in ratios. Like V2 is 20 times of V1. Okay, so you can calculate that. The second one is root mean square speed. So you will be using this equation that's given. So I think one common mistake is the molar mass or molar weight here is given as 1.008. So some of you guys didn't convert it into kilograms. Okay, so this one you would convert into kilograms. This one, I think we went through this in class one time. So the gas will expand, the tank will expand, but less than the gas. Okay, so then you'll take the difference of the two for the gas spill. Delta T will be the same, V will be the same. Okay, now these are coefficient of volume expansions. They are given. Okay, the temperatures they are given in Fahrenheit though. Okay, so it's not in Celsius or Kelvin. So you can calculate difference and then convert it into Celsius. So just the difference you will just multiply by 5/9 of it, of 24 multiplied by 5/9 give you the difference in temperature in Celsius. Okay. Number 4, this is about a calorimeter. You have a metal and a gas, water mixing them together. So you add the heat change of the two to be 0, and then you can solve for the T. T will be the only unknown there. Okay. On this one, this is also like one of the labs you did for the standing wave. So basically, you'll be calculating first the wavelengths. So it tells you 3 loops are measured. So then it's 3 halves of lambda. Okay, that equals that guy gives you lambda there. Now you can calculate what's the speed of this wave in the stream by using this equation. Once you have that, then frequency can be calculated. Okay, so speed divided by lambda will give you frequency. Number 6, I think you have one of the problems in the homework like this one. So the bat is giving out frequency, and then the moth. So there are two parts of this problem. So the first is the bat is the source giving out the frequency. Now the moth is the receiver. Okay, so after the sound hit the moth, then it will reflect back. So then in that case, the moth now is the source, the bat is the receiver. So you want to apply Doppler's effect twice. So if you do this, you can apply this twice, okay? Or you can just put them together. Also, this is like doing it twice. So then give you the final frequency there, okay? So apply Doppler's effect twice there. And this one 7 is on sound level, okay? and then intensity. So 200 pairs, then will be 200 I for intensity of one pair. Okay, so basically then you can follow that. Number 8 is the hot air balloon problem. Okay, so buoyant force should be equal to the weight, both the hot balloon and passenger, and then plus the weight of the air inside it. Okay, so then that's the free body diagram over there. You can set it up so you can solve for it. Okay, you'll be so there's several different ways you can solve for this one, but the solution I give here is I first solve set up this is the buoyant force equal to the weight of the balloon and passenger plus the weight of the air inside it. Okay, so then I can calculate what's the density of the air inside. And from there, I can calculate what's the mass of it. Okay, so then I know what's the mole of it, dividing the molar mass of it. So then go back to PV equal to nRT, I can calculate the temperature. Okay. All right. This one is on number 9 is on the um, entropy change. Okay, so entropy change for this. Oh, actually, no, it's not entropy. Yeah, I guess we haven't talk about entropy. So this is just about on the heat change of the material, but in this case, the specific heat capacitance is heat capacity is a function of time t. So then you'll have to do integration of it. Okay. All right. Number 10, there's one problem in the homework similar to this one. So you have water and ice mixed together. So you can calculate what's the amount of heat for water to go to 0 and then compare to the amount of heat to bring the ice to 0. Okay. So first you calculate those two heat, you figure that this guy is less than that. So then ice will melt. Then the latent heat for ice melt, it's actually greater than the heat of this guy. Okay, so that means Q1 plus Q2 is greater than QW, the absolute value of it. So then it tells you your ice just melt partially. Okay, so you still will have ice and water mixture in this case. So your final temperature will be 0. All right. All right. Any questions you guys might have on this? Okay. So if not, then let's take a look on the lecture part here. So homework 4 is due on Tuesday, okay? Oh, actually Wednesday. Yeah, it should be Wednesday. Okay, next Wednesday. For in-seat classroom disinfection, it's Owen and Jeffrey that I assigned to today, okay? All right, so last time we start chapter 4 and then we talk about irreversible and reversible processes. So pretty much everything happens in this universe they are irreversible processes, okay? So in ideal situation, you might have reversible process, but in reality, it's very hard to find a reversible process, okay? So the second law of thermodynamics says heat will transfer from hot object to cold object spontaneously. Okay, and later I think we learned that you actually could reverse the heat transfer by adding extra work to it. Okay, but naturally that's the way it goes. We also took a look at heat engine. So for heat engine, because of the heat can flow from hot object to cold object, then you can take part of the heat, convert into mechanical energy, and then that's what the heat engine does. Okay. three components for a heat engine. There should be a hot temperature reservoir, cold temperature reservoir, and a engine that does work. Okay, so QH will be equal to QC plus W. All right. The efficiency of the engine is defined by how much work can be done divided by the heat it takes in. So W over QH, and W is equal to QH minus QC. So you can write this expression, or 1 minus QC over QH. Okay. So I have several different expressions there you can take. All right. And so for heat to flow from a cold temperature object to a hot temperature object, then you will add extra work. So that's the mechanism for a heat pump or a refrigerator. So it actually does that. Okay. So it brings heat from cold temperature object to a hot temperature object here for a refrigerator with the extra work done by the this refrigerator here. Okay, electric work comes in and then takes heat from the food and then dump the heat to the kitchen. All right. Efficiency, or we call it coefficient of performance of the refrigerator, is defined by how much heat you can remove divided by the work needed. Okay, so KR or COP is equal to QC over W. For air conditioner, it's basically the same as the AC, or the same as the refrigerator. Okay, it takes heat from the cold reservoir and then with the work done here, and then dump the heat to the outside environment, the hot reservoir. Okay, heat pump does the same thing, but in the reverse process of AC, where this time heat is removed from the outside cold temperature, cold air, and then with the work done from the heat pump and dumped to the inside air. Okay. So coefficient of performance for heat pump then would be QH over W, because you want to have QH added to the room given the work done. Okay. So all these appliances you want, if you are shopping for them, you want to look for higher numbers on the coefficient of performance. Okay. And then we took a look on two more statements on the second law of thermodynamics. So for a perfect heat engine that converts 100% of heat into mechanical work, that's not possible. Okay. Also, the other way around, if you want to just remove the heat and then dump it to the outside environment without adding work, that's not all possible. Okay. That's not also not possible. Okay. So there are those two statements there. Today, so as I mentioned just earlier in a previous slide, you cannot convert all the heat it takes in into mechanical work. So that means your efficiency for the engine couldn't be 100%. Okay, but what's the highest possible efficiency you can get? Okay, so assuming that all these processes happens very slowly for a cycle. Okay, so if you start from M, goes down here, and then so this is isothermal expansion process. So it goes from here, start from here, isothermal process, and then adiabatic expansion further expanded, and then compression process here, and then goes here, another compression process, and return to its initial states. Okay, so this is a cycle here. So if all this happens slowly, you can treat them as a reversible process. Okay, so that's the ideal case. What happens to the work and how much heat it takes in? So what's the relationship of the two? And then we can calculate what would be the highest possible efficiency you could have for an ideal engine like this. Okay, so it's called a Carnot cycle. Okay, for ideal cycle. So a little bit review here. So when you have an isothermal expansion, the work done is equal to you can start from here, but for isothermal process, T is equal to constant, okay? So P then will be equal to nRT over VE. So the work done will be nRT ln of V final over V initial, okay? So this is for isothermal process. So for an adiabatic process, we derived this earlier, and then let's see. And then at the end, we say you can write the equation, an equation like this or equation like that. Okay, so if you have T, just in terms of T and V or P and V, so those are two equations you can write. So these two equations are derived with the additional help of this guy. So this is ideal gas law here. Okay, so then you can use any of the two parameters to describe an adiabatic process. Okay. So let's take a look. If you have those four slow process like quasi-static reversible process, then what you have, okay? So the heat it takes in, so if this is isothermal process, all right? Isothermal process means the internal energy is equal to 0, change is equal to 0, so then Q is equal to the work done, okay? So according to first law, so QH it takes in is equal to W1. That would be nRTH, okay? TH is the temperature, the high temperature of this process, okay? Line of V final minus V initial. So this is final, this is initial, okay? Now for the adiabatic process of this guy, okay, you can write in this term. So TV gamma minus 1 equal to constant, okay? So you start from N and at O, so that means T at N will be the TH, okay, times Vm, okay, initial, gamma minus 1 equals to Ct, at this point should be the Tc of this process, this isothermal process, okay, so that's the code. Vo as at that point, V final, gamma minus 1, okay. Similarly, for isothermal compression, you can apply the same equation as the isothermal expansion, okay. So Qc will be equal to, in this time, is nRTc ln of V initial divided by V final, okay. So in that case, it goes from here to there. Or actually, it could be, it should be just minus. All right. But I think we are going to look at the absolute values here. Okay. So then when you take absolute value, you can do V initial minus V final, because then this will give you a positive number. Okay. VO is greater than VP. Okay. For adiabatic compression, this process you can write similar term to this guy. Okay. So initial T initial V initial gamma minus 1 equal to T final V final gamma minus 1. All right. So then if we look at, so let's, if you are taking notes, just make sure this is absolute value of QC and absolute value of QH, okay? So absolute value of QC divided by QH, absolute value, should be equal to, all right? So this term over that term, right? So then NR will cancel out. So then it will be just TC line of this guy over TH line of that guy, okay? Now, if you go to look at these two equation here, only the two adiabatic processes, this guy and this guy, okay? So if you do, or if you can rearrange the term, you will find, so if you do TH over TC is going to be equal to VO divided by Vn gamma to minus 1, okay? And then also from this one, you can write the same. You'll find that will get the relationship of this guy from these two equations, okay? This one and that one. You'll get this VO over VP is equal to Vn over Vm, okay? So then basically it says the line on the numerator is equal to the line in the denominator, okay? So then the line function will go away. So it will tell you the QC and QH is equal to TC over TH, okay, the absolute values, all right? So the heat dumped to the environment divided by the heat it takes in is equal to the temperature of the cold reservoir, which is the environment, divided by the temperature of the hot reservoir, okay? So that's what you are going to conclude, okay? Or, yeah, so this will go away. Then QC over QH is equal to TC over TH, or QC over TC is equal to QH over TH. So either way, okay? You can write it in that way. All right. So then for a Carnot engine, an ideal engine, okay? So efficiency is equal to 1 minus QC over QH. One of the expressions for the efficiency can be written as in terms of just the temperatures, okay? 1 minus TC over TH, all right? So you can see it's equal to that guy. Now remember when you, so this is one of the very common mistakes people make. So when you are plugging TC over TH here, both of them should be in Kelvin, okay? In the SI units of Kelvin. All right. So let's take a look on this first example here on a Carnot engine. Its efficiency here. It says Carnot engine takes 2,000 joules of heat from a reservoir at 500 K and does some work and discards some heat to a reservoir at 350 K. What's its efficiency? How much work does it do? And how much heat does it discard? All right. So I think you guys can give it a try, and then we can take a look at the solution together. All right. So let's take a look here together. So it's a Carnot engine, so you can calculate efficiency by using 1 minus TC over TH, okay? So the two temperatures are already given in SI in the SI unit of Kelvin. You can put them directly in. Okay, so that should give you 0.300 or 30%. Okay. Okay. And the second, you'll be looking for how much work does it do. So then E is also defined as work over QH. Okay. It tells you QH, then you can solve for W. So W then will be equal to E times QH. So 0.3 times the 2000 joules. That will give you 600 joules. Okay. That's how much work is done. The last is looking for QC, so that would be QH minus W. Okay, that would be 2000 minus 600. Okay, so 1400 for that. Okay. Let me know if you have questions on that. All right. So if not, then we are going to move on here. So then, similarly, if you have an ideal refrigerator, so then it goes just the reverse process. Okay, so it goes from P takes heat this way. So it's the reverse of this process that we saw earlier, the reverse cyclic process. Okay, you can do the same mathematically. You can prove that QC over QH is equal to TC over TH in this case again. Okay, so then the coefficient of performance for a refrigerator, which is QC over W. W can be written in terms of QH minus QC. All right. So then, because QC over QH is equal to TC over TH, then this can be written as TC over TH minus TC. Okay. For a refrigerator, the Carnot refrigerator. Okay. And then for a heat pump, then it would be TH on the top instead of TC, because for heat pump it's QH on the top. Okay. TH divided by TH minus TC. All right. So Carnot's principle, so basically for Carnot engines or Carnot refrigerator, Carnot heat pumps, you can calculate what's the theoretically highest efficiency, okay? But the Carnot's principle basically says for real engine, it's going to be less than that Carnot efficiency or Carnot coefficient of performance that you could have, okay? So all right. So some other applications for power plants. So far, most of the power plants we have are still thermal power plants. That means it's working between two temperature reservoir, a hot reservoir and a cold reservoir. Okay, so the hot reservoir is typically heated by fuel, either it's from a coal or like nuclear reaction. All right, so then that gives the heat in here, drives the turbine here, doing mechanical work that is converted to electricity by a generator there, okay? And then dump the excess heat to the coal reservoir, the condenser, okay? So for power plants, thermal power plant, you can calculate what would be the maximum or Carnot efficiency by using this equation again, okay? So it will be TH minus TC, which give you, or this is similar to 1 minus TC over TH, okay? For nuclear power plants, it works similarly, just for the heat in takes in, it's from the nuclear reaction, okay, that generates a lot of heat that's being used to heat up the steam there. And then it will go through the turbine here doing mechanical work that is being converted to electricity by the generator there, okay? And then you typically see larger cooling towers. That's where the excess heat is being dumped to, okay? So these are the towers, okay? All right. So any questions you guys might have on the previous section here before we move on the Carnot engine and then the thermal power plants? All right. So if not, then we'll take a look on the next section here about entropy, okay? So we derived that for a Carnot engine, QC over QH is equal to TC over TH, or if you rewrite this, is QC over TC equal to QH over TH, okay? So now there's these two quantities, Q and T, on the same object. So the cold reservoir here and then the hot reservoir, they're equal to each other, okay? So typically what we like to do in physics is if you have combination of certain quantities, that would be equal to one status equal to the other status, then we'll define that as a new parameter. So here we call this as entropy. So Q over A over T is defined as the entropy change, okay? All right, so delta S equal to Q over T. That's called entropy change. In differentiation form, then you'll be doing derivative of S equal to derivative of Q over T, okay? All right, so we just gave out the definition for entropy change. Let's take a look on a simple example here. It says a heat engine operates between two temperature reservoirs, the hot reservoir and cold reservoir. Temperatures are given. In one particular cycle, the engine absorbs 6,400 joules of heat from the high temperature reservoir, and that's 2,200 joules of work. What's the net change in entropy as a result of this cycle? All right. So I think we will take a look on this one here, okay? So it tells us QH is equal to 6,400 joules. It tells us that it does 2,200 joules of work, right? So then for QC, you can calculate it. Should be 6,400 minus 2,200 will be 4,200 joules, okay? Now we are looking for what's the entropy change of this process, okay? So there's this hot reservoir TH gives out QH, and then there's this engine does amount of work here, dumped QC to this TC. All right. So delta S equals to Q over T. Right, that's the entropy change definition. So let's take a look on what's the total entropy change here. We should account entropy change from this guy, the hot reservoir, right? So then, and then also the heat change for this cold reservoir, right? So just Q over T. This is W. It's not related to, or it's not Q, so we don't count that one there. It doesn't have a temperature even, so you probably just wouldn't count on that one too. Okay, so there'll be entropy change for this guy. There'll be entropy change for this guy. Okay, so delta S1 and delta S2. Okay, or let's say delta SH, delta S sub C. So then total should be equal to delta SH plus delta SC, right? Now we want to pay attention to the heat, the sign of the heat here, okay? So for the hot reservoir, it loses heat, okay? So that means when you plug in the number for Q here, so this will be Q, will be minus Q of H over TH, okay? And then plus for the cold reservoir, it receives heat. So its heat change will be positive, just the QC over TC, okay? So this would be minus 6,400 joules over 610, that's already in Kelvin, plus 4,200 over 320 Kelvin, okay? So then the two will add up to be 2.66 joules per Kelvin, okay? So here's something you want to pay attention to, the heat, okay, the signs for the heat. When we talk about just the engine, when we calculate the efficiency, we actually don't care about the sign, okay? But when you are doing the entropy change, okay, that means change in Q over T, or Q over T, that means change in Q, okay? The change in heat, okay? So then you want to put appropriate sign, okay? So that guy is negative of Q there. Just want to highlight that, okay? All right. Any questions you guys might have on this one? Yes. So this is the total entropy change, the number. It actually means the disorderness. So the disorderness of the system will increase. So in reality, the entropy change will not be negative. Okay, just keep that in mind. If you get total entropy change on the system. So if you are looking at individual ones, they might be negative, but the total should be positive or at most zero. Okay, zero refers to the ideal situation, okay, which actually in reality never happens, but in theory it could be. Okay. All right. Okay. We'll take a look on a second one here on the entropy change here. So this one says compute the change in entropy of 1 kilogram of water with its temperature increasing from 15 grams, 50 degrees Celsius to 100 degrees Celsius. Take the specific heat capacity of water to be 4186 joules per Kelvin times kilogram. All right, so you guys may think about how you want to do this, and then we will take a look at the solution together. Okay. Now this is a different this one is different from the one above it. Okay. So the one before, previous one, we checked the temperature of the objects is not changing. In this case, the temperature of the water is actually changing. And we are just checking on the change in entropy of the water. Okay, so we just Q or delta S for this for water. Okay. So it's going to be dq over t, and then you are doing integration of it. Okay, because t is changing here. You will go from 15 degrees Celsius to 100 degrees Celsius. But when you do that, you want to put the SI unit here. Okay, so 15 degrees, that means 15 plus 273.15. And then on the top here should be 100 plus that. Also for dq, it should be equal to mc times dt. All right, and then you can replace dq with this expression there. All right, so let's take a look here. So when temperature is changing, you want to use this expression. Okay, otherwise you can just use delta S equal to delta Q over T. Okay, if temperature is not changing. Okay, if temperature is changing, you use this. If otherwise, you use that. Okay, so in this case, your temperature of water is changing. So we'll use this guy. So delta S then equals to integration from this to that. So 288.15. That's 15 plus 273.15. Okay. On top here should be 373.15. dQ, according to specific heat capacity, should be the mass of water times specific heat times dt. Okay, so mc dt over t. All right, t is the variable here. mc, m and c, they are constants, so that should be equal to mc ln of t. Okay, and then going from 288.15, that's in Kelvin, to 373.15 in Kelvin. Okay, so it'll be mc times line of 373.15 minus line of 288.15. Okay, m is 1, c is 4186. Okay, multiply by that. All right, so this minus that you can write as line. If you want, you can write as line of 373.15 Kelvin over 288.15 Kelvin. Okay, in that expression, then K and K will cancel out. You don't worry about the temperature there. Okay, so it will show you that this and that will cancel out, but this will give you 1082 joules per Kelvin for the entropy change of the water. Okay. All right. Questions you guys might have? So if not, then we are going to take a look on entropy change of an ideal gas. Okay, so for ideal gas, you can apply that first law of thermodynamics. Okay, so change in internal energy is equal to change in heat minus change in the work done by the gas. Also, PV equal to nRT or nKT would apply here. So then ds, according to the definition, equal to dq over t in this case. Okay, so then you can write delta S will be integration of ds. Okay, which is integration of that guy. So dq over t comes from two parts. Okay, so let's see. One part is from that guy. Do I have one more slice here? Actually not. All right, so let me show you where the result is from. Okay, so from the first law of thermodynamics, you can write dq from the first equation there. So dq then equals to dE plus dW. Okay, from this guy here. All right, now for ideal gas, E internal energy is just equal to CV times dt. Okay, or if you write this as small c, then you put the n in front. Okay, I think we have capital C here. Okay, so then we don't put that. And plus this is PdV. Okay, or actually dW, we just write as dW here. All right, so then when you do now, you do dq over t, this will be equal to CV dt over t plus dW over t. Okay. Then you do integration here for delta S. Okay, integration here, integration there. So this guy, the first term will be straightforward. So CV of T2, natural logarithm of T2 over T1. Okay, because you have that. So ln of T, and then upper limits minus lower limits. Okay, plus this guy. Okay, so this is for dW, all right? So dW work done. Let me see if this is from dW is PdV. So you put that in that expression. All right. So on the second part here, this is dW there. So dW over T is equal to P over T dV. Okay. Now P over T from here, PV equal to nRT. So P over T will be equal to nR over V. Okay. So this is nR over V dV. Okay. So then this guy becomes that guy. So if I do integration to this, okay, again, it's dv over v. So then it will be giving you a natural logarithm function. Okay. So this is from, this is dw over t. Okay. If you integrate that, will give you nr natural logarithm of v1, v2, which gives you nr ln of v2 over v1. Okay. So that's where the second term is coming from. Okay, so for ideal gas, its entropy change you can calculate with this one plus that one. Okay, for any ideal gas. All right. Then so now it depends on what process you have. If you have isothermal expansion, so then T will be constant. Okay, so then the first term will go away. So delta S then will be just equal to the second term. All right. And for Q, because T is constant, so internal energy change is 0, it's equal to T. Internal energy change, internal energy is proportional to T. If no T change, then that's 0. So Q equal to W. Okay. So that's that case there. And in that case, the surrounding loses heat, Q. All right. So then the total entropy change for the surrounding and the gas. This is the gas, this is the surrounding. Okay. Will add up to be equal to 0 because this is that guy. All right. Plus minus of Q. This divided by T will be the same as that. So positive plus and minus equal to 0. Okay. So then this is for a isothermal expansion. Okay, so for the reversible isothermal expansion, you have entropy change equal to 0. Okay. See, we have made quite a few assumptions here. First, it's ideal gas. Okay, and then it's isothermal expansion. In reality, that's probably not the case. Okay, either way, it's not the case. All right. So entropy change for this process, though, if it expands, all right, so then it's equal to, this is isothermal expansion because it's vacuum over here. So then the temperature is not changing. So delta S will be equal to this guy, okay, which will be greater than 0, okay. So for the total entropy change will be just for the gas, and then expand to this side of vacuum. If this is well insulated, okay, so it's going to be equal to 0. Now you can see this is not a reversible process, right? The after this expansion happens, the gas will not go back to the left chamber without doing any work. Okay, so this is not a reversible. It's not a reversible process. Okay, so delta S will be greater than 0. Okay. All right. There's one example here. I don't think we have time for that, but let's talk about the entropy change. Okay, so entropy change for a given system, a given object is Q over T. So what happens if temperature goes to 0? All right. In reality, it doesn't happen. Okay, so any object will not reach absolute 0. Okay, so in reality, that's not happening. That's basically the third law of thermodynamics. Okay, so for any object in the universe, you cannot have its temperature equal to absolute 0. You can approach it very closely. I think the best we can do is 10 to the minus. I don't remember the number, but maybe in 10 to the minus 20 something. Okay, very close to 0, but not possible. Okay, all right. So let me see. So I think, yeah, we'll just stop here. Okay, for today.